Welcome to Science Saturday. Today we are going to be learning about magnets, which are really cool. I have here some ceramic magnets which are encased in a layer of plastic. You can see that if I take off the top layer, the ceramic magnet is just a piece of iron metal that has been magnetized, but it's kind of brittle. It will crack and break easily, and that's why a lot of times when you buy ceramic magnets, they have some sort of case over the top, a plastic case, to protect that magnet from breaking. Well, if you have played with magnets at all, you are aware that they have a really cool property of being attracted to each other and attracted to a lot of metal things. So for example, these magnets here, if I line them up underneath like this, I can make this top magnet move back and forth across the surface of the book without touching it, just by moving this magnet on the bottom. But check out what happens if I turn this one upside down and then it flips over. I'll do that again. Oh, I made it fall off. It's a little tricky because that repelling force is strong enough that if you come up slowly, a lot of times it will just scoot to the side. And if you come up too fast, you can usually get them to flip around or jump around and move, because they do not want to be, there we go, that was a good one. They don't want to be touching. Those opposite sides don't want to touch. So magnets that are lined up like this are very strongly attracted to each other, but if you flip them around so the orientation is the reverse, they repel each other, and that repelling force can be really strong. If I want to touch the blue on the blue, I have to push together and then I have to hold really strong, and if I let go at all, then they flip around to go the other way. Have you ever wondered why magnets are magnetic? What things are attracted to a magnet? How you can make a magnet? Well, that's what we're going to discover in this Science Saturday lesson, and we're going to do it with several fun activities. For our first activity, I have 2 magnets on either side of the ruler, and then I have 5 little hexagonal shaped nuts that are made out of steel. And I'm going to attach them to the magnet, and you can see that because they are the right type of metal, they're attracted to the magnet and they're all sticking together. But the magnetic field doesn't just affect things that are touching the magnet, it affects things that are around the magnet. And I can prove it to you by just slowly lowering these down and balancing them on the edge of the cup. I think my magnet isn't quite lined up. There we go. If you're trying this at home, I'll just give you a heads up. This can be a little bit tricky because you really need to make sure that the magnet is exactly above the edge of the cup. If you're a little too far forward or back, then the nuts will fall. But they're staying here now because of that magnetic field that's coming from the magnet, and it's strong enough and special enough that it doesn't have to be touching the nuts, and it doesn't matter if I interfere with it by running my finger through it here. I can block it with my finger or my hand, and it still is supporting those little nuts and keeping them in place. But if I raise the ruler just a little bit, they all drop. Magnetism is such a cool phenomenon. To really understand it, you have to dive deep into quantum physics, and we're not going to get all the way there today, but we are going to explore which things are magnetic and which aren't, and talk a little bit about why. Check this out. I have 4 metal objects here, and can you guess in advance which ones will be attracted to the magnet and which ones will not? You already know that the little hex nut is going to lift up and be attracted to the magnet because it's made out of steel, and the activity that we did before, we showed you that these little things made out of steel are attracted to magnets. What about the pop can? No. The pop can is made out of aluminum, and it is not at all magnetic. It will not be attracted to the magnet at all. Next, I have a nickel, and the nickel is not magnetic. This American nickel 5-cent piece is actually made mostly of copper, and copper is not a magnetic metal. But this Canadian nickel is actually made mostly of nickel, and so it is attracted to the magnet. Only a few elements are strongly magnetic, and we're going to find out which ones they are with some little element cubes that I have. All right, first we have aluminum, and just like before with the pop can, you know already aluminum is not going to be magnetic. Neither is cadmium, chromium, or copper, but cobalt is. Cobalt is magnetic. Let's keep on going down our line. We have iron, which is magnetic and attracted to our magnet. Nickel, and I already told you from that Canadian nickel that nickel is a magnetic element as well. But titanium and zinc and pretty much every other metal and non-metal really are not magnetic. And the question is why? Why are some metals magnetic and other metals not? And for that, you need to know just a little bit about electrons. This is a little bit of an oversimplification, but you can think of each electron as being like a miniature magnet. And most of the time, electrons come in pairs. And when they're together in pairs, it's kind of like they cancel each other out. So then you don't really have a magnetic charge. But with these three metals, with iron, cobalt, and nickel, you have a special condition where you have an electron that is not in a pair. And if you have enough of those together, like a whole bunch of iron atoms together, and they're all lined up in the same direction, then they create a magnetic field. And this is pretty cool because this means that you can take pretty much anything that is made from iron, cobalt, or nickel, and you can make it into a magnet just by exposing it to a magnetic field. So if I have two paper clips here, right now these paper clips are not at all magnetic. But if I take one of them and I keep it next to a magnet for a long period of time, and usually this takes several minutes, I will get all of those electrons lined up in the same direction and the paper clip itself will become magnetic. A few seconds of exposure to the magnetic field with this paperclip was not enough to turn it into a magnet, but there's a way that we can speed up the process and make it more effective if we use electricity. Check this out. So I have a large nail here, and right now it is not at all magnetized. If I put it in this box of paper clips here, it does not pick up any of the paper clips. But I have a copper wire around this nail, and if I put the ends of the copper wire on a battery, then very quickly that will change. The electrical current that is running through this nail is going to magnetize it. It's going to get all those electrons lined up in the right direction. And now if I want to try and pick up paper clips, I can. I've just turned this nail into a pretty effective magnet, even without the battery being attached. Now I'm still able to pick up a paper clip with this nail that just a few seconds ago was not at all magnetized, and that's all because of running a current through it. The interesting thing about this electromagnet we just made is that it is not a permanent magnet. When the current is running through it, it will pick up paper clips really well, but a few hours later, it won't pick them up at all. This nail is made out of iron, and remember we said that the electrons that are in iron, they have that cool ability to be oriented and have a little magnetic charge. Every single electron you can kind of think of as being a miniature magnet. In the iron, they exist in these little domains where some of them have a charge pointing one direction, others of them have developed a little bit of a charge pointing the other direction, and the overall effect is that all of the domains cancel each other out because they're just done at random, and there really is no overall magnetism that takes place in a regular piece of iron. But when we run a current through it, what we do is that electric current makes all of the domains line up in the same direction so that then we do have a magnetic field. Now here's the thing about electrons in a metal. They are very fluid and they can move around a lot. That's why metals are such good conductors of electricity. And once that electric current is removed, there's nothing in there to hold the electrons in place. And so they turn back to our nail not being a magnet anymore. If you want to make a permanent magnet, other things have to be added. You have to add something else in place that will help make that structure a little more crystalline, a little more regular and rigid, and that's why magnets tend to be brittle and easily broken. We can use electricity to make something metal a magnet, but we can also use magnets to generate electricity. This is something that we do all the time in hydroelectric dams and with things like crank-powered flashlights. This is an emergency-powered flashlight. If I turn the button on and then start to spin it, you can see that the light gets brighter and brighter the more I spin it, and then if I stop spinning, the light will dim and eventually go out. All of the power and the electricity in this flashlight is generated from spinning a magnet. The more you spin it, the more light you have, and eventually the light will run down. Well, I cut open an identical flashlight so you could see how it works, because this is pretty cool. So we have our handle, and the handle is connected to a magnet. When the handle is being spun, the magnet spins inside a coil of wire, and that gathers electric charge. The electrical charge is then passed through other wires down to the bulbs, And there is an on-off switch in a little box that can disconnect or connect wires, so you can store up charge with this little tiny rechargeable battery here, or you can just have it power straight through depending on whether this on or off button is switched or not. So in a nutshell, that's how a crank-powered flashlight works. Remember, there are three elements we talked about that are magnetic: iron, cobalt, and nickel. Iron is the one that is perhaps the most important to us. Not only is it abundant and probably one of the most common metals that we use, but it's also very important for our nutrition. If you don't have enough iron in your diet, then you are not going to have the ability to carry oxygen to all of your cells. You'll get what we call anemia, and that can be really damaging and have some health effects with it. And so our breakfast cereals are fortified with iron. And what we're going to do next is extract the iron using a magnet so that we can see how much iron is in 2 cups of this breakfast cereal. I just added equal parts of water and cereal to this blender. We're going to let it sit for several minutes before we put it in a bag and extract the iron. But while we're waiting for it to soften, let me talk to you a little bit about the differences between magnets, because as you may have noticed, some magnets are a lot stronger than others. One of the most common types of strong magnets you'll see is called a neodymium magnet. So here in my pocket I have a relatively small neodymium magnet. Most of it is covered in this little plastic casing. You can see that this ceramic magnet is a lot larger than the neodymium magnet, so you might think that it would be able to pick up something heavier, but that's not the case. So here I have a can of corn that weighs just over 16 ounces. That is much heavier than either of these magnets, but this neodymium magnet in particular is very light. It's half as light as this heavier ceramic magnet. If I set it on top here, I can pick up the whole can of soup with this magnet. It's about the heaviest amount that I can pick up with this magnet, but that's very impressive. Ceramic magnet, on the other hand, if I try and pick up the can of soup, there's no way. I would need a huge ceramic magnet to be able to pick up this much weight, whereas this little neodymium magnet handles it with no problem. When we do our iron extraction with the breakfast cereal, you are really going to want a neodymium magnet, because you need a magnet that is strong enough to really pull those iron pieces toward it. A ceramic magnet is not going to be strong enough, and you'll be very frustrated if you spend hours going over the bag with a ceramic magnet and you don't see any iron and nothing happens. So, neodymium magnet, that's the type that you need. All right, now we'll blend up our cereal and pour it into the bag. You want to get as much of the air out as possible. Now I'm going to set this on a white poster board so you can see it a little bit better. As I mentioned before, if you are using a ceramic magnet, you will drag it across for a long time. You know, you can do this for hours, and you're going to gather very little iron, and it'll be frustrating for you. But if you use a neodymium magnet, just one slow swipe across, and you should see iron particles. That little dark line there are pieces of iron that have been attracted to the neodymium magnet. And even a small neodymium magnet will work. This tiny little fridge magnet that I have, if I'm somewhat patient, and I drag it across a few times, I also will find little particles of iron. That's a little bit of iron that was gathered by this small magnet. Now what you want to do is just bring this magnet across and get all of your iron on the one side of the bag. Now that you've gotten a lot of it over to this side, we can start here and just very slowly bring it all the way down to the corner. There we go. That is the iron that was in this 2 cups of breakfast cereal. Thank you for watching this episode of Science Saturday. There is a little coloring page about the Earth being a magnet that you can check out over at patreon.com/sciencemom. Thank you to our patrons for supporting this science outreach. And instead of our safety song, I have a little fun fact about a magnet coming up. And I'd love it for you to tell me if at the end of these videos you prefer to have a safety song or a fun fact. Let me know in the comments. We'll see you next week. Did you know that the ink that's used in US currency is magnetic to help prevent counterfeiting? If you have a dollar bill and you hold a magnet to it, you can see that the dollar bill is attracted to the magnet. It's not super strong. I mean, this isn't super magnetic ink, but there's enough magnetism in it that it lifts up and is attracted to the magnet. Pretty cool, right?